Okay, so it's great to have you all with us, students, faculty, friends of friends. This is a continuation of our series of colloquia, CAMS colloquia, which are delivered essentially by CAMS fellows. Okay, so every year we go through a process of selections of CAMS fellows, and the ones who are selected propose projects on which they want to work. And we invite them to give a review for a broad and technical audience on their field of research. So a review of the field itself, and then some details, a bit more technical, on their actual contributions to it and their plans for the fellowship. So this year we had a diverse group of fellows with a variety of applications, mostly actually concerned with data as it happens, okay, from a variety of fields of engineering, physics, and applied mathematics. We also have the pleasure of having people who applied from outside AUB. That's also a new thing for us, and this is a very interesting, a very promising form of collaboration. So the series will kick off with a contribution by Dr. Joseph Bakarji, whom I had the pleasure of knowing and I look forward to interacting with over the coming few months. So he's a postdoctoral fellow at the AI Institute in Dynamic Systems at the University of Washington, but he's also around and has contributed some mini courses on some matters related to his work already within the Department of Mechanical Engineering here at AUB. He's a CAMS fellow with us for the year or longer, and there are discussions of activities and plans that he will be, announcing shortly. So it's a pleasure to introduce Joseph in a field which is gaining a lot of interest, traction, and many applications, and which is also of great relevance to many of our colleagues here at AUB and outside. So basically, if I were to put it succinctly, physics can sometimes lead to complexity when you have the mathematical models for what's going on. And sometimes also you're dealing with complexity at the level of observations without access to the equations, the governing equations, or suitable models for the governing equations. And we spend a lot of time trying to a mixture of guesswork, intuition, symmetry considerations to refine models that are of use in describing physical reality. With machine learning, there's been quite a bit of progress on using data as a driver to constrain models. Some very successful, some raising a lot of questions, but certainly quite a promising direction of work, which in many ways goes back to the early days of dynamical system theory. So it's a pleasure to have Joseph walking us through the field from his perspective, as well as his direct contributions to it. Thank you, Joseph.
Thank you, Jihad, for this great introduction. Can you hear me? All right. Thank you all for being here. Really exciting to be here. So today I'm going to tell you about using machine learning to discover physics from data. Very exciting new field that I got introduced to during my PhD. My background was in mechanical engineering, but I've always been fascinated by physical modeling in general. And so lately, I've been mostly working on discovering mathematical laws in general from data. So before anyone asks me why use machine learning to discover physics from data, what's wrong with brains? I'd like to kind of motivate the use of machine learning in physical modeling. And I want to say something like a small confession, which is that I'm not specifically interested in physics or in biology or any specific strain of science. I'm more interested in what is physics. And that question, which sounds very philosophical, has become more relevant recently because of things not working. Okay, see how it works. So the question is, of course, this is a big question. What is physics in the first place? And now the question is, why is this question relevant in the first place? Well, the fascinating thing about the question for me is that there's this reality which is supposed to be infinite. There's this known part of reality that we know from the past experience, and there's this unknown part. And what science and physics in particular does is it takes in this known reality and compresses into some scribbles on a paper we call math. And somehow those scribbles, we can manipulate them, and we can use them to reconstruct and predict reality. So we can foresee the future by just somehow taking this reality, compressing it into simple symbols, and then using those symbols to make predictions. That's the question that's interesting. And you can see how that question doesn't apply only to physics, but applies to science in general. And it becomes even more interesting that when we represent things properly, that math is part of reality. It's not something outside of reality. Of course, that becomes a bit philosophical. Some people might disagree. But the idea is that we're taking that infinite dimensional reality, compressing it into something simple, and using these simple laws to make predictions. And it becomes also very interesting when you consider that as for the case of language, not only math, and for the fact that this relationship exists in time as well. We take past observations, and we use, in our present moment, we use these observations to make predictions in the future and to act on the future. So you can see how a question about physics, what is physics, leads to a question about intelligence. What is intelligence? So the big questions that I'm interested in answering is what is it that we do when we do science? Why? Because if we want to automate the process of scientific discovery, we need to understand how it works. And then can we build scientist machines? For these are sort of big dreams and claims that will never happen, probably. We will never be able to answer these questions, but this is the general direction in which we're heading. And to answer this question, I want to also take you through a brief history of science, where machine learning fits in the history of science. So we have this, as I said, infinite reality, part of which we know, part of which we don't. And historically, we learned how to quantify that reality by transforming it into numbers. Galileo is one of the pioneering first figures who did that, but of course there were people before him. And then we took that data and compressed it even further into these simple models, like Newton did and Leibniz, for example. And then we use these models, we manipulate these models to predict data that we haven't seen yet, and then we project that back on the world. So traditionally, we've done the modeling by hand, where we manipulate these mathematical laws, we integrate them, we define differential equations, etc., to make predictions. But recently, starting around the 1950s, with computers coming into play, we learned how to solve differential equations and solve these models and build these complex models and solve them numerically using computers. So this opened the door to a completely new world where we can understand more complex, more nonlinear, and more high-dimensional systems. And now, in the past 10 to 20 years, computers became so fast that we can also go from the data to the modeling. So it's really mainly a function of the fact that we have a lot of data and that computers are much faster. And now also we quantify the world at an increasingly exponential rate because we have the internet and we have devices that collect data constantly. So you can see how this whole modeling process is a form of compression. We're compressing a high-dimensional world into low-dimensional simple equations, and that the purpose of getting these models is to really solve them and reconstruct the world so that we can predict things that we haven't seen yet. And one thing is for sure is we're going to have many more computers in the future. And another thing is that they're probably not going to look like this. So how do we, now you might ask, well, still this doesn't convince me that machine learning is necessary for doing science. Why don't we do physics and science the way we've always done it? Well, think of the earliest scientific laws. How did people do science in the first place? think of Pascal's law, Hooke's law, all the empirical laws that we've been exposed to during undergrad or even high school. And you will see a pattern. They're all linear. They all relate some kind of flow quantity with some kind of potential quantity. And they're really a matter of designing experiments in such a way that you can somehow fit the line between these two quantities. We can control one and see the effect on another. And this is how we define viscosity, elasticity, etc. Of course, you might say ideal gas law is a bit more complicated. Well, if you look at the history also, you can see that scientists like Boyle found the relationship between P and V, and then Charles' law, etc. So all of these were linear relationships, and then they were kind of merged into this ideal gas law later. So laws can be thought of as linear fits, where, let's say in the case of Darcy's law, you have a porous medium, you pass in a fluid from one side, comes out the other side, and you apply a certain pressure, and then you can collect data. You have an experiment set up where you collect data, you have pressure in, pressure out, and then the volume flow rate. And based on that table of data, you try to fit a model that takes in the pressure difference and gives you the flux. So at the end of the day, this is a sort of linear fit. And this is kind of another perspective of looking at physics as sort of a form of at least empirical laws, as a form of machine learning, where the machine doesn't exist yet, but we're just fitting models to data, mathematical laws to data. All right. Now, linear laws are great, but we're usually interested in much more complicated equations. Particularly, we can maybe summarize the history of science as the discovery, or specifically physics, the discovery of differential equations that look a bit like this. They could be, it's an ODE, but they could be PDEs, dx dt equals some f of x. And the art is in discovering the right variables x. What do we need to measure? And to find models f that predict those variables x. So again, what we did, we took observations, and by hand, we tried to model these differential equations. And then we also made sure that these differential equations can be solved by hand so that we can actually validate them with predictions. So we take in models, we compress them into these differential equations, we solve them, and we get the predictions x. But the problem is that these x's can be really high dimensional. For example, let's say we're trying to predict what the atmosphere is going to do. So weather prediction. Or we're trying to look at the soil. We're trying to predict earthquakes. So all of these involve a lot of variables. We're not sure how many variables they involve. And even when we do, they're very high dimensional. Another complexity is that these functions f can be highly nonlinear as well. In the early days of science, these high dimensional nonlinear equations were ignored because there's nothing you can do about it when you're solving things by hand and when you're modeling things by hand. But when computers came along in the 50s, it's become possible to actually take these high-dimensional nonlinear differential equations that we can build and solve them. But instead of doing it by hand, we do them numerically. And this completely changed the game. For example, this is, at least in my research, in engineering and a lot of sciences, a lot of research goes into first building these complex nonlinear models and simulating them to see if they match reality. So this is a microfluidic transistor, which is a microfluidic channel with a nonlinear elastic membrane on top of it. And it behaves in a way like a transistor, but there's fluid structure interaction. These things cannot actually be modeled by hand. They can be approximated. This is what we did. But these approximations can only be validated with simulations. So this was not possible before computers. Of course, you can get into more sophisticated models like social dynamics, where you assume some kind of interaction laws between the members of society. And the society affects the contaminants in an aquifer, and that contaminant, then they pump back the water and they use this water. And there's this feedback relationship between these two very complex systems. And now you can also simulate these types of systems. Of course, they're all approximations, but you can match those approximations with data from the real world. And of course, you can also do multi-scale modeling, where you couple continuum to discrete models. These are SDEs and PDEs, stochastic differential equations, partial differential equations. I'm not going to go into details, but the point here is to show you that you have these complex models that, we have equations for them, which seems like it's enough to understand what's happening, but that's not enough in most high-dimensional complex systems, because you need to actually solve these equations to understand them. If you have an equation, it doesn't mean you have understanding of the behavior of the system. And of course, this is a problem I spent a lot of time on, which is a multi-scale modeling of granular materials. These are interacting grains. We understand the interaction between the grains pretty well, but when we put thousands of those together and we try to compress them, and they're heterogeneous, there are shock waves traveling through them, you have these nasty partial differential equations that you need to solve. It becomes even hard to solve these equations. So reduced order models become important, and all of that is in the context of computational modeling. So the bottom line is complex systems have uncertain models. They can be very high dimensional and uncertain. They sometimes have uncertain parameters and sometimes even uncertain computational schemes. So we can push this computational framework enough that at some point, having the laws is not enough, the fundamental laws. So sometimes now we have the data, but we don't have the necessary laws to describe the system. We have partial knowledge of the models and partial knowledge from the data. So how do we combine these? It's not working. Okay, I can do that. Okay. So, well, with computers becoming much more powerful, now we can go from the observations to the models, which is exactly what I'm going to be talking about today. And we do that by doing some kind of regression. We're minimizing, we have the data, the observations, and we're trying to find the best f that gives us this differential equation, given these observations. So we're minimizing the difference between x dot and f of x. It's a kind of regression. So it's an optimization problem. We transform the process of scientific discovery into some kind of regression. And traditionally, we did solve these differential equations through integration. But now the computers are so powerful, we can also do that through regression as well. So we can find the best x that fits x dot equals f of x. So you can see how the first part, historically, we automated this part, which is solving the differential equations numerically. And now we're getting more and more into this part, which is discovering the differential equations from the observations. Now, connected to what I talked about earlier, this is really, again, a compression reconstruction framework where we're taking something that's high dimensional, a lot of data. We're trying to compress it, distill it down into a simple differential equation. And we really want that differential equation to, when we solve it, to give us back the predictions and to generalize over things that we haven't seen yet. Just like physical laws. Yes. It doesn't have to be infinite. It's finite. It's just very high. So yes. So if, for example, you discretize, if you have a PDE and you discretize it, you get F as the discretization of the PDE on a grid. This doesn't assume a grid, but it could include the fact that you have a grid. Does that make sense? But it's not infinite dimension. I'm not talking about infinite dimension F. Although it's possible to talk about it, but here it's finite dimension. So this is also kind of pushing it even further. You can see that there's a parallel between this compression reconstruction framework and scientific modeling with how brains do things, which is they take very high dimensional observations from the real world. They compress them into models that they can use through perception, that they can use to act on the world in the future. So there's a parallel there as well. All right, let's get into more technical details. So historically, this has started a while back with expert systems when people started doing artificial intelligence in the 50s. But exploring these models to actually discover physical laws from the data started with the Bacon system with Patrick Langley in 1977, and then more recently with Eureka and AI Feynman. These are algorithms that basically take data that's related to physics. Maybe they take it from a physics textbook, and then from the data they try to infer the equation. And then they try to infer usually equations that we already know. So the task here is to discover an algorithm that rediscovers physics. And symbolic regression has been one of the first systems to do so. And it assumes that equations are trees. So let's say this equation, y equals 2z minus sine of 3z. You can actually cast this equation in terms of a tree. So you have this minus sign that connects these two parts of the equation. And then here you have 2 times z, and on the right you have sine of 3z. Right? So if you can now represent an equation as a tree, what you can do is, what we're trying to find is the best tree that can fit this data. How do we do that? Well, we take that tree and then we start changing things in that tree. So one way to do it is genetic algorithms. So these, you can think of these equations as trees, and you can start mutating these parts of trees. For example, you can change the minus to a plus and see what happens. You can create multiple trees. For example, this tree, which is z plus 5, and this other tree, which is still what we presented earlier. You can crossbreed them. You can take part of that tree, put it here, and then crossbreed them in a way. So you can think of equations as species or genes, and they're mutating and crossbreeding just like species do. This is how genetic algorithms work. And by doing so, you're sort of optimizing for the best equation. It's an efficient way of searching through an infinite dimensional set of equations, so that at the end you get this line that fits best the data. Now, genetic algorithms accelerate that process, but it's still a pretty slow process. So these can discover very complex equations in the sense that you can have sine of cosine of 3z raised to the power n, etc. But it takes a very, very long time to converge to something useful. So if you have a differential equation that has multiple terms, like Navier-Stokes equation, for example, then it can take a really long time. So for that, there are other methods that do better. There's also a recent method that was discovered a few years ago called physics-informed neural networks. And the idea here is that you know the differential equation, some nonlinear differential equation relating to some nonlinear operator, and you have some measurements from the field. So this is x and t, and these are measurements. They're red dots, so they don't have to be a lot of measurements. And the idea is that you're not very certain that this is the right equation. Maybe it is the right equation, but there are some heterogeneities in the field that may adjust the equation. And you have some measurements that can inform that adjustment. And what you want to do is you want to find this nonlinear function that connects the inputs x and t to the output u. So you're trying to approximate the solution u of xt. And to do so, you minimize this loss function. This really looks a bit complicated, but all it is you're trying to minimize the difference between the data points and the solution. So this is the first term, to be consistent with the measurements. The second term, you want to be consistent with the boundary conditions and the initial conditions. So you also take points at the boundaries of this domain, and you put it in your loss function. Again, you're solving an optimization problem. And the third term is you put in this equation in the loss function. So you can put the residual of the equation in the loss function so that it is also satisfied. So you're satisfying measurements, equation, and boundary initial conditions, which is what you need. Usually, if you're just solving the equations forward, you're satisfying only these two, boundary initial conditions and equation. But here you have this extra perk of also satisfying measurements. So this is another technique of combining knowledge from data with knowledge of the physics. And these, I didn't say that these require collocation points. You just throw in a bunch of points in the domain, and then you try to satisfy the residual, this term, on these points. And then the other method, which has also become very common in recent years, and which a lot of my recent work is based on, is the sparse identification of nonlinear dynamics. So I'm going to take you through also how that works in more detail, to the example of the heat diffusion through a rod. So we all know that you can take a metallic rod, can impose some temperature boundary conditions, and then heat will diffuse through that rod. What is the equation that governs heat diffusion through a rod? Anyone remembers? No? Okay. Let's say you don't remember, but I give you access to a lab where there's a rod and you have a bunch of sensors that you can measure the temperature at different points in the domain, right? So you have x1, x2, up to x8, so 8 points in the domain. And you can measure the temperature at t0, time 0. And you can do it at time 1, time 2, etc., up to time n. Right? So now you have measurements for a bunch of points in time and a bunch of points in x. So this is space-time domain. And based on these data points, you want to discover what's the differential equation related to it. What would you do? Based on the data, you want to extract the physics. The first thing you assume, you have to assume something. And the first thing you assume is that the change of the temperature in time is somehow related to the change of the temperature in space. And the relationship you're not certain of, it's some function of the change, the first derivative in space, second derivative in space, maybe some nonlinear term. You throw in whatever you think is relevant or could be relevant. And what you want to do is you want to discover what the relationship is and what the coefficients are. So the first assumption we're going to make is we're going to calculate the derivatives of the temperature in time for a given point in that domain. And we're going to put it in this form. So the change of temperature with respect to time, this derivative is calculated numerically. And then this is the change with respect to second derivative, first derivative, etc. And we're going to say that there's a linear relationship between these two sides. So the temperature dt is equal to a dot product between this set of coefficients and this set of differential terms. And this is the nice thing about differential equations, that they apply everywhere in the domain, right? They're true everywhere in the domain. So this equation is true for that specific point. And for the next point, if I just move a little bit, for that point, if also I calculate these terms, I should have the same coefficients, C1 to Cn. And if I do it for another point, I'll also do the same. So now I collect all these data points I have, put them in this big matrix. And now I have this column vector is equal to this theta matrix times this vector, C1 to Cn. Now, I don't know what this C1 to Cn is. But the whole point here is I want to find this C vector that satisfies, that best fits the data that I have. And this can be expressed like this. I want to find the optimal C such that I minimize the difference between the left-hand side of this equation and the right-hand side of this equation. Derivative of temperature and time minus theta C. So this is L2 norm, minimizing difference squared, and then we find the best fit. But now the key element to understand in this method is that it wouldn't work unless we have this extra term in the loss function, which is the sparsity term. So this also minimizes the number of terms that I'm looking for in the equation. I want the simplest equation possible. So remember the idea that we're taking something really high dimensional and complicated, trying to compress it into as simple an equation as possible. So this is what this term does. It's an L0 term, which means we're maximizing the number of zeros. And what we're looking for at the end is an equation that looks like this. It's a diffusion equation where C1 will be non-zero and everything else will be zero. So this is how this method works, the sparse identification of nonlinear dynamics. And you can imagine how this can be useful for cases where we don't know what the equations are, but we have access to the data. And then from the data, we can infer what the equations are, just given some assumption about the form of the equation with unknown terms. And so now to go a little bit more into the technical details, so I'm going to tell you about 3 applications that use this idea discovering differential equations from data. First, to do coarse graining, to go from small scale to large scale models. Second, to discover models from partial measurements. So it's very common in complex systems or high dimensional systems that only have access to a few measurements, but the real system actually it has to be described by more variables. So how do we do that? And the third case is discover dimensionless groups from data. This is like Reynolds number, Mach number. If you're not familiar with those, I'll go through that briefly. Now, one thing people discovered in the past few years is that if you just apply these machine learning algorithms as a black box neural network or this equation discovery, you're not going to have a lot of success because these optimization problems are very nonlinear. They're very hard to it's very hard to find the equation you're looking for. So constraints become very important. And in all of these, I'm going to show you how you can introduce knowledge from physics that you already know into these algorithms to give you something that makes more sense. So this is constrained machine learning, or as some people call it, physics-informed machine learning. So to start with the first part, question is, what do you think is the biggest problem in scientific modeling today? I know this is a very subjective question. I'll tell you what my answer is. Challenge, whatever you think. Error quantification. Yeah, that's definitely a very big problem. But my answer is scales. The biggest problem, which is probably not going to go away anytime soon, is how do we bridge the scales? We have models at very small scales, we have models at this scale, we have models at very large scales, and sometimes we can use the same models, but in most cases, especially when it comes to systems that combine all of these models, complex systems, we don't know how to do the bridging pretty well. And this is important, for example, for environmental modeling, modeling living organisms, biological modeling. All of the important problems involve scales, involve multiple scales, and we don't have an effective way of combining these scales other than sort of concatenating all these models together and simulating them on a computer and seeing what happens. So we don't have an analytical approach to that. We barely have a computational approach to that. So how are we to tackle these big challenges? Now, I'm not claiming that I'm going to solve this problem. I'm just saying it's important. But a start to solve this problem is there a way to go from one scale to another, from small scale, fine-grained simulations to large-scale simulations or large-scale models, here probability density function equations using these techniques I explained earlier. So, well, the story goes like this. The world is made of things. Some of you might not agree, of course, at small scale, probably they're not. But they're made of things, and these things interact. And sometimes we know the rules, and we can use those rules to predict the future. But the problem is that, in general, all things are made of smaller things, and they're fit in larger things as well. And we don't know how to go from smaller things to larger things in most cases. In some cases, we do, which is great. But in most cases, we don't. So statistical mechanics, we can learn a lot from that. But when it comes to complex systems, like granular materials, very simple building blocks, but complex when you put them together. Brains, pretty complicated building blocks, and even more complicated systems. And living organisms, of course, we don't even come close to understanding these because they involve a bunch of scales. So how do we tackle these? So all complex systems involve multiple scales, and with scales comes this problem of averaging. So we might know what happens at smaller scales, but there are multiple microstates that can correspond to only one macrostate. So when we do that averaging, we're losing information. So this is one of the biggest challenges. And the other challenge is that in these nonlinear and uncertain systems, even if you know somehow the initial condition, these can be very chaotic. So you cannot predict exactly what the future is going to look like. You can only predict the distribution. So uncertainty has to be accounted for. And therefore, modeling the probability density function becomes very important. working with probabilities rather than working with deterministic equations. And you can see how this structure of multi-scale modeling looks similar to the compression reconstruction framework I presented earlier, because upscaling, going from small scale to large scale, involves some kind of compression, and downscaling involves some kind of reconstruction. So it's ill-posed and it's complicated to do in general. So how do we do that using data-driven methods? Let's say you have a differential equation, du dt plus some nonlinear operator of u equals 0. And what you're looking for is an equation for the probability density function. Why? Because in this case, let's say you have uncertain initial conditions. So there's uncertainty. Or you have uncertain parameters. We don't know what the parameters are in most systems. So what we're doing here is we're coarse-graining in probability space, right? We're going from a random u to a deterministic f that is a function of u. So to do that, there are analytical methods to do that, like the PDF method, for example. But in most cases, you get closure terms. So you cannot actually close the equations to solve them. So an alternative is you take this equation and you solve it using Monte Carlo simulations by sampling from the uncertainties. You have uncertain initial conditions, you sample from that and you get a bunch of realizations. And from those realizations, you approximate the PDF numerically using current density estimation. So you can take these realizations that are random, and you can get the PDF numerically from them. And then from that approximation of F, you can use the sparse identification technique that I presented earlier, find an equation for F. So we did a small detour and we used a data-driven method to discover the equation F rather than doing an analytical approach. Now you can actually just discover the whole equation, which means we're trying to discover this operator L. And by assuming that L has some form, some derivative of F in X and capital U, because now F is a function of the sample space variable U, or in some cases where I just mentioned earlier that you get closure problems, so you'll do the derivation by hand, and then you get stuck at some point where you have some terms that you know that you could actually derive by hand, but some terms that you don't, and you try to discover these terms, the ones that you don't know. Now, this applies not only to coarse graining in probability space. So we have a great example here at AU of people who are trying to do coarse graining for active matter. This is an example of active systems like fish schooling. I don't think Sarah is doing fish. Oh, she's doing fish schooling. So fish schooling and marathon runners and a bunch of other examples, which are really exciting. So in this case, what you're trying to do is, you know that there is some kind of rule that governs the interaction between these active systems, and you're pretty sure this sort of coarse grains into some general continuous equation, but you don't know how to do it analytically. So we try to use these techniques to discover the differential equation. Another one is granular materials, a project I'm currently involved in, where you have these force chains and really complex structures that happen at the small scale. So it's not clear what the constitutive law relating the stresses to the strain are. So analytical techniques also fail in this case to a certain extent. And this is an ambitious project to take a lot of EEG data and then try to infer what are the large scale dynamics of brains, at least depending on what the forcings are from outside. And I'm going to briefly go through this the techniques here. The general technique here is you do some Monte Carlo simulations. So you collect U using these uncertain initial conditions. So you have fine-grained data, and then you approximate the PDF using current density estimation. And then you approximate these derivatives of the PDF with respect to space, X, whatever dependent variables you have, independent variables you have. And then in this specific case, because we're trying to find a PDF equation, we have information of what PDF equations, the constraints they have to undergo. One of them is that the PDF always integrates to 1. So it has to be a conservative equation. And the other is that in the case of a PDF equation, you cannot have derivatives higher than second order. You actually can. But if you do, then your PDF might become negative, which is reasonable. So to constrain the PDF to be always positive, you use this theorem, and therefore you don't have to assume a bunch of infinitely many libraries. You can only include derivatives up to second order. So this is where knowledge from the physics or from the context of the equation helps you constrain your machine learning algorithm. And this is sort of how you should always think about the problem when you use machine learning. So, okay, this equation, you don't have to actually look at it, but all this is the residual of your differential equation. And all this is we're defining it in terms of a matrix. And at the end, we're just trying to find the coefficients that minimize the residual. If you're interested in the math, just there's this paper from 2021 goes through the details of what I'm showing here. To give you a simple example, let's say you have this advection equation with a nonlinear forcing. This develops a shock. And you have uncertain initial conditions, u of x, u0 of x. So in this case, you can generate Monte Carlo simulations with uncertain initial conditions. And from those, you approximate the PDF. And from the approximation, you actually learn the equation for the PDF. In this case, it turns out we can actually also do it analytically, which means we can validate that the algorithm works. These coefficients, by the way, should be 1 u squared and 2 u, but it's pretty close. I think we just leave the rounding to the humans. Maybe that's at least humans can do something. It's good. So, all right. So we talked about discovering PDF equations and coarse graining using machine learning. What's next? Well, the second problem we always face is that in some systems, they're very high dimensional, like atmospheric dynamics. I like to give this example because it's pretty high dimensional. Here I'm just saying it's three-dimensional. So this is a chaotic system that's three-dimensional. That can be written as an ODE this way, but it's nonlinear and has a fractal structure, very interesting system called Lorentz system. But let's say you have this high-dimensional, in this case, three-dimensional system, and you're just making measurements. Somehow you only have access to the first dimension. You only have access to Z1, which here I'm calling Y, your measurement. Is there a way for you to take this Y of t and go back to reconstructing this Z system, right? You can imagine how this is very relevant in a lot of physical systems where you just put a few sensors in the atmosphere and you're expected to predict the weather. To do so, you need to actually understand the equations for the whole high-dimensional system. Is it possible? This seems like a very ill-posed problem, but I'm going to show you how we can actually start to solve that problem by looking at the interesting theorem called Tauken's theorem. So what Tauken's theorem does, it says that if you take these measurements and you embed them in a high-dimensional space, I'll tell you what this means. Time delay embed them in high-dimensional space. There's a nonlinear transform that takes you from that embedding to the original system, to original high-dimensional system. And then we also know that if you have z of t, we can discover some function z dot equals f of z using the sparse identification technique I talked about earlier. But the whole thing about this method is Tauken's theorem that tells you that there is this mapping and this interesting transform for the data that allows you to do that. So what is this exactly doing? So let's say you have y of t, you have this time series, it's discretized, and I'm going to just take 4 points in this time series. Y of t plus tau, y of t plus 2 tau, y of t plus 3 tau. I'm going to take these 4 points and embed them or project them or put them in another coordinate system where y of t plus 2 plus tau plus 2 tau plus 3 tau are the axes in this case. So what happens is we're taking 4 points in this time series and transforming them into 1 point in a 4-dimensional system. So 4 points in 1D become 1 point in 4D. Right? So, and you can imagine we can take more delays. These taus, n tau can be pretty large, can be 100 dimensional. So we can take a window of 100 data points and project them on 1 point in a 100-dimensional system. So this is time delay embedding. Now, why are we doing this? Well, because of the theorem. The theorem says that if we look at the original full state coordinates that we're trying to find, there's a non-linear and continuous transform that can take you from that embedding back to the full state coordinates. So that's what the theorem says. It says that the transform, the nonlinear transform exists, and it's continuous, and we should be able to find it. It doesn't say what that transform is analytically. It doesn't even derive it for any specific system. It just proves the existence. And then we also, of course, are interested in finding a differential equation for that system once we find the coordinates. So to develop our method, we start from here. We say we have this differential equation. We just take Z1 as a measurement, and then we do that time delay embedding. We do the diffeomorphism, and we try to find. So there are two things we're trying to fit here: this F that maps Z to Z dot, and this diffeomorphism, this nonlinear transform. Okay, so we're trying to close this loop. And whenever, nowadays someone tells you it's a high dimensional nonlinear transform, you immediately think of a neural network, because a neural network can allow for these high dimensional approximations and nonlinear approximations. So we show actually that if you know both sides of if you know the data and delay coordinates and full state coordinates, the neural network does an amazing job at doing that fitting. The neural networks do work in this case. But what we're interested in is doing both the transform, discovering the transform along with the equations where we don't know what Z1, Z2, Z3 look like. So what we do is, let's say here we have a full state system, we take measurement Y, and then we time delay embedded, it becomes this variable H, and we use an autoencoder. This takes an H, compresses it down into Z variable, and then maps it back up from Z to H. So we have these two fitting functions, phi and C, which are supposed to be inverses to each other. And we're also trying to find an equation for Z in the latent variable, this hidden variable that we're trying to discover. We're also trying to find Z dot equals F of Z, where we can control what F looks like. So in this case, in the Lorentz case, we can constrain F to be a polynomial differential equation because we know it's going to be some kind of polynomial. And this lets us converge to a Z that makes sense when it comes to the data. So spoiler, what we get at the end is this covered differential equation, which doesn't look exactly like the original one, but has 3 parameters. It's sparse because this is another thing we're constraining. And when you simulate it, it's also chaotic and has this butterfly shape, right? And tells you a lot about the dynamics, the fact that it's chaotic, that it's not just a random time series. Now, this architecture is being used not only for this specific application where you have the time delay embedding in the input, but let's say you have a high dimensional video. So you have video of a pendulum, and you can take the video of a pendulum to compress it down into some variables here that follow the dynamics of the pendulum. So this has been done in this other paper. And this is an active area of research that tries to find a coordinate transformation, or here a dimensionality reduction, along with the equations in this lower dimensions. So you're optimizing for both coordinate transformation along with the equation in the new coordinate system. All right, so this is an example where you have a video. This is called the Lorentz water wheel. The angular velocity of the Lorentz water wheel actually follows the Lorentz, is one of the variables in the Lorentz system. And then here what we did is we extracted the angular velocity from the video. This is what we took that from YouTube. And then we extract the angular velocity. And from the angular velocity, we apply the algorithm. And we get back this butterfly-shaped dynamics for the Lorentz system. But in this case, it's very noisy. As you can see, this algorithm that detects lines is not perfect. It's not even, the video is not taken, it's taken at an angle. So it's very noisy and you have a lot of problems. So in order to get a stable dynamical system, what you end up with is not very sparse. You get these small turns that make sure that you stabilize the dynamics. So this means that this is still an active area of research where we want to find better algorithms that can take these types of dynamical systems and videos. And you can imagine these videos don't have to be actually videos. They can be, pictures, satellite images of the ocean, for example, that can measure velocity field. So you can take these high dimensional systems, compress them down into low dimensional data, and then from them extract the equations. The last thing, so I leave 5 minutes for questions, so I'll briefly tell you about this third project, which is for extracting dimensionless groups from data. So far we've talked about systems where we know what the variables, the relevant variables are. In many cases, we have the variables, but we don't know how these variables are involved in the dynamics. We don't even know which data to collect. And this is where dimensionless groups come in very handy, because they don't actually involve data. They don't need data. And they tell you a lot about the qualitative behavior of the system. For example, what's the difference between a flying hummingbird and a swimming microorganism, right? The difference is not in the laws that govern the fluid around them, because they're both governed by the Navier-Stokes equation. The difference is just in one number, the Reynolds number. These swim at a very low Reynolds number, so they experience the fluid with much higher forces, much higher viscosity in a way. The fluid resists them at higher forces, and for a hummingbird, the fluid is completely different. So we don't actually need to know the Navier-Stokes equation to understand the qualitative behavior of both of these systems. And these dimensionless groups, Reynolds number, actually determine, you have whole fields that study low Reynolds number, large Reynolds number. So they also, divide the scientific fields into different sub areas. So they're very useful. And if you don't know what dimensionless groups are, just to mention, they're basically unitless. So you can take these variables that are involved in dynamics, density, velocity, distance, scale, and viscosity. And if you multiply them and divide them in this way, while each of them has a certain units, when you do them, when you multiply them this way, you'll get a unitless number, the Reynolds number. And fluid dynamics and physics is full of these dimensionless groups, and they're all very important to tell you something about the system. Now, there is a method to actually extract dimensionless groups given the variables that are involved and parameters. And this is called the Buckingham Pi theorem. The Buckingham Pi theorem tells you that given some inputs P and outputs Q, and there's some kind of mapping F between the inputs and the outputs, let's say the inputs are viscosity, density, and the output is the velocity of your flow field, and F is usually the solution of your differential equation. The Buckingham Pi theorem says you can transform these variables into dimensionless variables, pi p and pi q, that now the solution space is lower dimensional. So you have less variables involved. So it's a lossless kind of dimensionality reduction through some variable change. And the theorem says that there also is a mapping in this case between pi p and pi q through this function c, but doesn't say what that function c is. The other flaw with the theorem, it's not a flaw, it's just that it doesn't work out that way, is that it's not unique. So it says there is that mapping, it gives you the mechanics to do that, but you need to make assumptions to actually get to a unique solution. So in most cases, when you have a lot of variables, this mapping is not unique. So what we want to do is we want to find this mapping informed by the data, such that these dimensional groups are relevant to the dynamics. Right? So we have a turbulent flow field. We want to actually get the Reynolds number to be in these dimensional groups. Now, just a little bit of math. If we concatenate these dimensional variables into P tilde, we know that there is this relationship between the dimensional variables and the dimensionless ones, such that there's this power phi ij, these powers that we're looking for. For example, in the Reynolds number, this phi ij matrix contains 1, 1, 1, minus 1, where you have a rho to the 1, b to the 1, d to the 1 divided by the reason I'm defining this is we can also define this dimensional matrix. And this matrix contains information about the units of the variables involved. For example, if you have a force that's involved, you have mass length divided by t squared. Every row here will represent mass length and t. So the first column will be omega of f will be 1, 1 minus 2. So for all the variables, you'll get different omegas. So I'm taking you through this math because what the Buckingham pi theorem breaks down to is just this equation. V phi is equal to 0. Phi, remember, is the powers of the dimensional variables that are involved in the transformation. And this also means that knowing D, you know D, but you don't know phi. So what phi is, it's a matrix that lives in the null space of D. So every column of phi lives in the null space of D. And the null space can give you many, infinitely many solutions. So what we're going to do is we're going to use this equation to find the best phi given the data. And the hypothesis is that the optimal set of dimensionless groups is minimizing this loss function that maps the dimensionless inputs to the dimensionless outputs through this fitting function C that the theorem doesn't tell us what it is. And we're also trying to find the best set of dimensionless groups that minimizes all of this loss function. So there are double minimization problem. And it's a form of finding hidden variables that give us the best and the most optimal or the simplest mapping between the inputs and the outputs involved. So this is the hypothesis that we're making, and we're going to test it on a bunch of problems to see if it applies. Now, this is still not enough to apply our problem. Again, we want d phi to be equal to 0, and we want this relationship. We want to minimize this relationship subject to that constraint. So how do we combine these two? So to do that, we have developed three methods to do that. And I'm not going to have time to go through all of them. I'll just show you one briefly, which is the first, constraint optimization with the non-parametric C. And then the second one involves a neural network, where we're finding a hidden layer, which is dimensionless. And the third one gives us an equation that's dimensionless with dimensionless parameters as well. So you get two in one, the equation and the dimensionless groups as well. Kind of an exciting direction as well. So for the first case, this looks like a complicated equation, but actually this term just tells you about the mapping between the dimensional inputs and the dimensionless outputs. Dimensional inputs and dimensionless inputs. And then here, the dimensionless outputs are already non-dimensionalized. And these are regularization terms. And you can see that b phi equals 0 is a constraint here. It's a hard constraint. So we're doing a constraint optimization problem. And C is a non-parametric Gaussian radial basis function, and we're using kernel ridge regression to do the optimization. The point is that when we do that optimization, we're actually looking for phi, powers of the dimensional groups that give us dimensionless groups, powers of dimensional variables that give us dimensional groups. And in the laminar boundary layer problem, there's a long history on finding how people discovered the equation for u of xy. So here you have a plate, and there's a flow field above the plate. It's a laminar flow field. And there's, u infinity is the velocity of the flow above that plate. And there's a non-slip boundary condition at the plate at 0. And Prempel discovered that you can actually write the equation for this flow field as this nonlinear PDE in the stream function. And later, Blasius discovered that if you just do a small change of variables, so you define this variable eta as y square root of u divided by nu x, then you can find an ODE. So you transform a nonlinear PDE. It's really hard to solve. Still really hard to solve, but ODE rather than PDE. And all it took to go from here to here is find this scaling parameter eta, which is also dimensionless. So can we use the algorithm I explained earlier to find this eta? Well, it's really close. So we get something that's very close. We just have to round the numbers of the powers to get to exactly 8. So this works when you're trying to find one dimensionless parameter. It also works for multiple ones in other methods I'll explain later. And if you look at the data, you can see how all the data collapse now to one line. So what the algorithm did is it collapsed the data to a lower dimension space, which is just one line. So we did that also to Rayleigh-Binar problem, which, if you're interested, you can also look at the paper, where we found the normal form for the bifurcation that takes you from just convection in the normal direction to these rolling the Scrolling behavior that's characteristic of the really binary problem. Okay, so I'm not going to spend too much time here because I'm out of time, and I will leave some time for questions. So all of these are examples of using machine learning to discover laws, but also being informed by constraints that we already know, in this case, these theorems. So this work was thanks to these collaborators, and these are the top 3 papers are about the work that I mentioned today, and that's it for today. Thank you.
Another wonderful overview, very rich set of problems. And put time for questions.
Yes.
The saying on presenting the meeting, instead of saying extracting physics from data, because people do say that goes somehow physics, right?
Yes.
So we are refining the physics and release.
Yes. Yeah, refining physics from data works as well. Sure.
So I have a question about token theorem.
Yeah.
You are doing a higher dimensional embedding, right? Time delay embedding to be able to reconstruct Z from Y.
Yes.
Does the existence of this time delay embedding relate to notions from control such as observability? Because this is observability, right? I mean, you have the output and you want to reconstruct the initial condition of your problem by having a lower dimensional measurement.
Yes, I am pretty sure there is a relationship, but the theorem actually doesn't go into that. The theorem says that if this time delay embedding is high dimensional enough, which I didn't mention, it has to be at least 2n+1 number of dimensions, where n is the dimension of the origin system. So in Lorentz case, it's 3 dimensions. The delay embedding has to be at least 7 dimensions. Other than that, it doesn't actually talk about observability. So what the data looks like. But I'm pretty sure that in some cases, you can have a data set where having more than 2n+1 dimensions is not enough. And the reason I think the theorem doesn't talk about observability is because it was originally applied to chaotic systems, more specifically to turbulence, where you don't have that problem in most cases. Well, at least in general, the general assumption is that you're going to get enough variability in the measurement that you're getting so that observability is not a problem. But that's a pretty good question, and I don't know what the relationship is in general, although there should be one.
Can we give the opportunity for those who are online? Maybe they have to leave. If you have questions, please unmute and ask. Okay,
Cynthia,
be with us. Any questions?
Yes.
yes, Cynthia.
Yes, Cynthia.
Hello.
Hello.
Thank you for the presentation. It was amazing, actually. What I wanted to ask you is not particularly relevant to the slides, because the explanation was very clear. I just was wondering to actually compile the algorithms and actually get what you want out of it. Do you have to use like clusters, supercomputers, any special tools to actually get things going?
Thank you, Cynthia.
Thank you, Cynthia. So very good question. And in most cases, I actually did the experiments on my laptop. So you don't in general need that, except in this middle case where we're trying to find these high dimension systems with autoencoders. And the reason here you need clusters and you need parallel computing is because you have a lot of hyperparameters. So you need to tune a lot of hyperparameters in the loss function, which ends up being very expensive for a laptop to do. So to do a single run for a given set of hyperparameters, it's pretty doable in a few hours. But if you're actually trying to find the best set of hyperparameters that give you a predictive model, then this becomes too expensive. But when it comes to Cindy, discovering differential equations, let's say in the heat equation problem, it runs in seconds, or even less than seconds. So that doesn't require a lot of computational power. And in the case of discovering dimensionless groups as well, it doesn't. So the only complexity is really just running these algorithms multiple times.
Actually, because when you first started your talk, you were the motivation of using machine learning was the fact that the computers are getting faster and more powerful. So I was just intrigued to where does the power of the computers come into play in things like this.
Yes.
Yeah.
Sorry. More questions. So yes, that's true. So in this case, you definitely need computation power. Also, in the so there's another thing that these don't use deep learning much. This one uses deep learning. When you get more and higher dimension systems, you start needing more computation powers. The other detail in these methods is that they all apply to toy problems. So when much higher dimension systems are involved, these will become much more expensive, which parallel computing becomes useful. And when it comes to discovering differential equations, you have these hyperparameters as well, which having a very fast solver allows, for example, these systems were really slow 20 years ago, so you couldn't actually work with them efficiently. So you just discover an equation, try to see which terms are involved, and then do that again and again. So it becomes a more interactive procedure when they're that fast.
Yeah.
Yeah.
Is it some information theoretic?
Yeah, so there are multiple techniques in general to do that. There's no single way to do it. So the choice of delta t and the number of dimensions. So the theorem also says that you have a minimum, but you can actually increase the number of dimensions. But let me just go to the slide to tell you a bit more. So here, so again, in this case, you need at least 7 dimensions because the origin system is 3. But you can go up to 100, like let's say. In this case, we use 120. But in general, the way experimentally people have found it works, because depending on the application, you're going to have to choose different time window. So I choose the time window to be around the period of oscillation. So in the case of the chaotic system, you have a period of oscillation. So you use this periodicity to be that, which means that n, the number of dimensions, times tau should be around the period. But there's no strict sort of rule on how to choose.
Yeah, that was particular to the Lorentz system.
Yes.
But for other arbitrary system with arbitrary attractors, there, I think, some information theoretic.
Yes, there's mutual
information.
So you can use mutual information to actually the general idea of choosing n and tau is in such a way that you unfold that attractor as much as possible in the delay coordinates. So you want the delay coordinates to fill as much as possible of the coordinate system, so that it becomes easier to map this data back to here. So you can imagine if it sort of all collapses to a line, that the data is all on a line, then the one-to-one mapping becomes impossible.
So is it implemented in the scheme that you have generally? Is it?
No, in my case, it's not. But actually, that was on the to-do list.
You might want to press that.
Thank you, Joseph.
Yeah.
I have a question concerning the physics-informed machine learning.
Yes.
So you mentioned the collocation points.
Yes.
So I'm wondering if your algorithm is sensitive to the number of collocation points. Is this some kind of grid whereby if you refine it, the optimization becomes better, or?
Yes. Good question. So number of collocation points definitely improves the result. So the more
do we have like in classical numerical schemes, do we have a sense of? No,
because this is not a grid. The collocation points are grid independent. So you just throw them randomly in the domain.
I'm aware of that, but is there any sense of understanding how does that affect your optimization?
I think there are studies. I'm not aware on the actual details of how the number of collocation points affect the actual result, but there is definitely a correlation. Yes. So one thing to mention, I've only used this method from the paper to validate, to like kind of learn about it, but I've never actually used it to discover something.
Okay, and I have a more general question. And
Yes.
so in this type of research, how do you validate? When you say it works well, I'm guessing that you are able to reproduce the data that you used, the sparse data that you used. So apart from the toy problems, is there any sense of measure of what does it mean to do well? How do you validate?
The general measure of to do well when it comes to, well, in this case, what you can do is, so machine learning, what you do is you split your data into training and test set, and based on how well you do on your test set, you determine whether you do well or not. Usually, sometimes this can also lead to overfitting, which means you do well on your test set, but when you try to apply it to some other data set, it doesn't work. But this is kind of an overarching problem of machine learning. In this case, what you can do is you can split your time domain into past and future, and you can say just have collocation points in the past. The problem here, and this method, I consider this method more of a solver than it is a way to predict things that you haven't seen yet. Because in general, it doesn't actually work when you don't have collocation points. So if you just learn U of xt based on these collocation points, and then I tell you, well, I have this data set here, does U generalize with the data in the future? It doesn't actually extrapolate well. So that's why you have to think about it more as a solver, because you say, I want to solve the differential equation in this domain up to here, so you just throw in collocation points everywhere. And then you have a better chance of converging. When it comes to SINDI, the sparse identification of differential equations, the purpose of the equation is to, when you solve it, it reproduces the data. So this is where you know that there's a success. So you have data set, also you split it into, and then you learn the equation based on one, and you try to see if you can predict the rest. That's the general approach.
The questions from the students? You're a student?
The question on, I mean, generally you're solving this optimization problem with different kind of regularization. How is the physics? I mean, how is it that you're tying physics with the kind of regularization? It could be an 1 norm or a 2 norm. So, and every regularization spits out different parameters. So how do you decide on?
Yes. So sadly, this is a hyperparameter, which means that you're going to get different solutions based on how you define your regularization. And again, you can do hyperparameter tuning or optimization if you have a clear objective. In the case of differential equations, the objective is to reproduce the data once you solve the differential equation. So this is where the choice of hyperparameters becomes important. So if you just do the optimization with the L1 norm, like here, why did I talk about that? Okay. Yeah. So if we look at this, if we just do this optimization, and then you're going to get some differential equation, right, with some coefficients. And based on this lambda, which is a hyperparameter that tells you how simple your equation is, you're going to get different equations. How do you decide this is good or not? You have to solve the equation. So, one technique to do that is to include in the loss function to make it a nonlinear optimization problem by integrating the differential equation and minimizing the difference between the integrated solution and the data. So this gives you much more robust, becomes much more robust to noise, and it somehow does the hyperparameter tuning for you to a certain extent.
Yeah. So Hiba, you want to ask you a question?
Yes, hello. Thank you for the very interesting talk. I'm curious about the step between, in the example of the Lorentz system, you create the embedding and then you look for a transformation.
Yes.
Using an autoencoder, and then you try to fit the model. And I'm wondering, because for example, if we're dealing with, if I already, and this is actually, I mean, when you have one-time series, it's pretty obvious why you would do that first step. But let's say I already have a kind of 100 observables. I have 100 times series.
Yep.
And so the first part of the question is the autoencoder step a kind of for the purpose of a dimensionality reduction per se, looking for a kind of, I mean, how does it compare to a nonlinear ICA where you use that neural network to extract these kind of minimal, lower dimensional latent variables? And in the case that you already start with 100 times series, would you still do the embedding? Because I know the embedding alone is, I mean, you have a lot of parameters and the whole different optimizations there in the first step.
Right, good question. So that's a good question that sort of is about the relationship between whether you have partial measurements, so it's low dimension, and you need to embed it to actually get to high dimension enough such that the relationship between an effective model and the input data is there's some kind of nonlinear mapping that gets you there. Or you have very high dimension data, which I mentioned, where you have a video, for example, that's really high dimensional. And what you're trying to do is just dimensionality reduction to get the effective variable. So that depends on the problem. Let's say if you have 100 measurements, but your actual system is can be described by 5 variables, then you don't actually need to do a time delay embedding. You just do the dimensionality reduction. When it comes to whether we should use the neural network or not, like nonlinear ICA or some kind of even PCA might be in some cases possible. For example, some people have done it where you time delay embed and then you use PCA or SVD to get to the dominant modes, and you try to do the modeling in after you do PCA for the dominant modes. That's possible. It's even in this case, for some chaotic systems, actually you don't need a neural network. You can have a nonlinear polynomial to do the mapping. So we also show that in recent work. So neural network is definitely not the only tool to do the nonlinear mapping. It's possible to do with the other ones, and it would be very interesting to try it with other ones in this problem, for example.
Are you satisfied, Eva?
Yes, thank you.
Thank you.
Any further questions from the audience? Leonie? No. So let me ask you a couple of questions, and then we'll see whether remote participants are stimulated. So I'm very interested in this approach to course grading. You discussed it briefly.
Yeah.
Okay, so you presented an example in which there are uncertainties in the initial conditions, let's say, which lead to a whole distribution of outcomes, trying to characterize equations that we cover in these PDFs, right? Yeah. And so, but in many cases, you start out with a finite n and you want to go to a continuum limit, and you need to course grade in some fashion, right? Yes. So you have these closure schemes as you described, and the whole question of closure is a very central and important question in fields of physics.
Yeah.
Now, you are proposing a scheme for coming up with partial differential equations that describe the PDFs based on data.
Yep.
Right. So ultimately, they are solving the closure problem in one way or the other. These PDFs that you're coming up with,
yeah,
have to be able to describe things beyond the mean field description to allow for
yes,
all of these interesting relaxation processes that you find very difficult to recover outside of closure schemes.
yes.
So any solution you come up with is effectively building a closure scheme or proposing a closure scheme.
Yeah.
Have you actually tried to think carefully about the solutions you obtain in relationship to closure schemes that one could deploy or prefer or favor?
Yes.
In the classical approach?
Right. No, we haven't done any of that yet, but that's a very interesting approach. We haven't actually made a lot of relationships between the unclosed terms, for example, and the discovery closed terms. That's something that we can do. And also the different closure approximations you can come up with. Some of them might be more accurate than others. And these can be parameterized, for example, in a way, so you can optimize over, what is the best approximation scheme given that data. So that's all assuming that you have enough data to approximate the PDF. And then you can sort of optimize the difference between the PDF that you get from the data and then the one you get from the approximation. So there are a lot of things to explore there. We haven't done anything.
I find this whole project quite exciting, and I want to definitely discuss it with you further. But I have another question on these parameter groupings that you described. So just so I understand, you have the equation, partial differential equation, etc. You have that. You start with.
Where? Which one?
When you're recovering the this parameters.
Yes, you do. Yeah.
So you start with equations, right?
So dimensionless.
It's not like I have a lot of simulations, or I'm trying to find out some meaningful groupings to collapse the data in some fashion or the other.
So here, what we did is we simulated the data.
So that's your toy problem. That's your formalism.
The formalism requires data. It doesn't require the equation.
It doesn't require it.
No. And the point here is that you find the dimensionless group given knowledge of the units of the variables involved and the data without knowledge of any of the equations. So we're not assuming the knowledge of the equations. And so in the third method that I mentioned, you discover the equation along with the dimensional groups, while you don't have the equations in the first place. But because of all of these are toy problems, they're actually solutions. So the data comes from solutions of the differential equations, where we add noise to them. And then we use that data to kind of get back the equation, reverse engineer the equations.
Yeah.
And
which raises a very general questions about all that you have presented today.
Yes.
It's so toy-based.
Yeah.
One is actually terrified. I think it relates to Leila's question. So what does it all mean? What does it all mean ultimately in the following sense?
Yeah.
Okay, so how do we decide in situations where we don't know anything that what you obtain is meaningful or useful?
Yes. So
Bakarji's theorem, okay, so we have some things that we can rely on, and the Kuplan transforms, we have things we can rely on. So we have various machinery we can rely on. But here we're going totally blind about it. Are there any assumptions you have to make about the physical reality that will guarantee a meaningful convergence or meaningful outcomes for the procedures that you described?
Yes. There are assumptions, obviously, like in the case of discovering differential equations, you have to assume which terms are involved. In the case of Tocquen's theorem, you have to assume number of dimensions, the architecture of your neural network. So all of these are things you have to work with. This is not a black box model where you just throw in the data and you expect something that makes sense to come out of it. The point from all of these algorithms is that they enhance their extra tools for scientists to use to get something that is meaningful. So it is, in a way, you're searching for an equation that describes your data, or you're searching for a closure problem, and you know that there are a bunch of hypotheses, and these could be infinitely many hypotheses, and you're just trying to optimize over these hypotheses. The more you add knowledge to the problem, the higher likelihood you're actually going to get to a solution. And these I presented here all toy problems because they're completely new algorithms that are applications of the sparse identification technique combined with a neural network to discover dimensional groups, etc. So the work that I've done so far is toy problem, but doesn't mean that this is all I'm interested in. So in fact, now we're actually just looking at real data where we can actually discover something that is useful.
So it all makes more follow-up talks by Joseph.
Exactly.
Around with us, also around for anybody who wants to solve, visit, discuss. Thank you very much, Joseph.
Thank you.
Thank you.
Thank you.